So in order to understand that, we have to understand the injury mechanisms. And a branch of study that deals with this kind of injury mechanisms is called biomechanics. You know, you might have studied solid mechanics in your engineering. You might have studied fluid mechanics. You know, similarly, this is biomechanics. It deals with the human body and their mechanics of it. So it's mainly similar principles are being used, and a lot of research has been done. It's extremely challenging to come up with proper data, but it has been done, and as it is being used, and a lot of research is still going on in the industry. A lot of universities are still involved in this kind of research. So what I want to do here now is just to give you a little bit of taste of biomechanics. So what exactly, how they came up with certain regulation, and how they calculate injury mechanism. How do you say that if this happened, you will die. If this data is less than this, you will be safe. You know, so it's all about a graph basically. You know, ultimately it is about a graph. You should be within these two values, then you are safe. If you go above it, you are dead, basically. You know, so how do you come up with that? You need a science backing it. So this is the biomechanics, that this is where it comes from. So this the what are we going to talk about? This is the one of the, this is called the head injury criteria, HIC, HIC, head injury criteria. uh, Very versatile injury criteria, very important, being used in all the standards, and very important if you understand it. If you go into this field, you will come across this term a lot, and the very first thing that you will have to learn is head injury criteria. So this curve here you see is called Wayne State tolerance curve. It's called so because it was first developed at the university called Wayne State University in Detroit, Michigan, and I have been very fortunate to study in that university. I studied biomechanics in that university. I studied under the professors who actually played very instrumental role in making this head injury criteria more stringent, more accurate, and more versatile and widely used in this. You will come across this curve also in your study if you choose to study it, and it is called Wayne State tolerance curve. So how did they come up with this curve? You know, so what they did, and this is I'm talking about in 1960s and 1950s, 1970s, that era. So they did cadaver heads. So cadaver is basically a dead body. They took heads of dead body and they dropped it on a flat surface from a different heights and different velocities. You know, so when they did that and they examined the fractures, the skull fractures. So when you say there is a skull fracture, it means it is fatal. When there is no skull fracture, it is not fatal. Now that is not very accurate, but still it was the best you could do at that time. Even today's time, that is the best you can do. There are reasons for it. And they came up with this curve. So this curve basically is the average acceleration and for how long that acceleration, the duration for which that acceleration is applied. You know, so basically it makes sense to you, right, that a very high acceleration for a very short duration, you know, it can be a life threatening, as well as very small acceleration for a very long duration of time. It can be like that. So this curve, any data that goes in this red region is considered life threatening. This curve is basically various fractures that were seen on the cadaver heads, and below this it's called not life threatening. You know? So based on this curve, they came up with this equation here. And how exactly they come? Did you see here? This is basically an integration of from T1 to T2 of acceleration. And here you see the power is 2.5. Now how they came up with 2.5 is basically, it's basically nothing but the power of this curve. This curve is a parabolic curve, you know, So y is equal to ax square. So instead of square, it is basically 2.5. They took a log of this curve and they found the slope and etc. They did a lot of mechanical mathematics on this curve. And after several years of this curve that came into picture, Japan also did the similar study. And lo and behold, they came up with the same curve and they came up with the same equation, So it's that, proven, this curve. So what this equation means is that you will have your acceleration curve, and for a certain time clip, for t2 minus t1, for certain time clip. So here it says the head, so this is basically linear acceleration. They were just simply dropped on a rigid plate. So it's a linear acceleration. The rotational acceleration is not taken into consideration in this. So when you do an analysis, you have your crash test done. What you do is you take the linear head acceleration, okay, you plot it, okay, so you will have some graph, there will be a peak and some graph will be there. What you do is for every 15 milliseconds, you divide that entire x-axis into 15 milliseconds, and in for every 15 millisecond you will average that acceleration, and when you average all the 15 millisecond intervals of the acceleration, the maximum that you will get should not exceed 700. That is your HIC, head injury criteria. Earlier it was 1000 for 36 millisecond clip, time clip. Now it is 700 for the 50 millisecond time clip. This is very stringent when you actually try to do this. So basically, if you have it 700 or less than 700, you can safely say that the occupant will not have any kind of skull fractures. So ergo, saying that they will not have any skull injuries. So hence there are chances that, and in today's time there are, and in US this 700 is the maximum limit. You cannot go beyond 700. Even if you have 701, your car will not pass for the front crash. It will not pass. You will not get any points for it. So we will look at this later also. Now, this is very versatile, but also there are drawbacks of this, that this only takes into consideration the linear acceleration and only talks about, it only gives indication of the skull fractures, because that's what the research was. It doesn't take into consideration the angular acceleration. The logic here was that if there is a skull fractures, there is obviously a greater injury inside, that is the brain. But you can have a brain injury without having any visible fractures on the skull. So that is a part of a mechanism that is still being studied. It is extremely difficult to study these cadaver studies. It's not easy. It's very difficult. We will talk about it later on why it is not easy. So this is basically a biomechanics. So this is just the head I'm talking about. Like this, there is a neck injury criteria. There is a chest injury criteria. It's called viscous criterion, and there is something for the abdomen as well. There is something for femur as well. There is something for pelvis as well. So from head to toe, everything has its own injury mechanisms. It is explored, and this field of biomechanics is not just used in occupant safety. It is also used for the sports. Sports is a huge market in United States and Europe. Sports like American football, which is like a rugby, and soccer, where all the athletes are sports persons are prone to a lot of injuries, and they want to design a very good helmet for them, so that they don't injure so well, and so many different kinds of gadgets they want to design. So that is where is also it is used. And yeah, so this is the field of biomechanics, and you will, if you wish to go into this field, you will come across a lot of these terms, and it will be very useful to study this. if you wish to. Uh, but this is not going to go away. This is the field is evergreen. It's the study of human body, and human body is different from region to region, and from age to age, from gender to gender. Now, based on these human biomechanics, these injury criterias, and based on the crashworthiness of the car, what kind of material, what is the kind of material you have to use, what kind of you cannot use, what is the permissible amount of energy inside the cabin, how to even reduce that. Based on all that, this is a nutshell of all the uh, crash regulations that exist in Europe, in USA, in China, in India, and United Nations. So can you imagine? It's too much for any manufacturer of car. This is just a lot, and it can happen that you follow one criteria and you lose certification in another criteria. So it has become more and more challenging in today's time to actually get your car certified in certain region for safety standards. It is a huge field of study. There is a huge market for it, and doing physical testing is equally hard. Can you imagine doing all this physical testing? How many cars you would need, you know, and high-end cars like Mercedes-Benz and all the others, Lamborghini and whatnot. Can you imagine doing so many crash tests? So that's huge investment, and you may never, you might have to repeat some of the tests, with the design modification, etc., etc. And this is where the finite element analysis comes very, very handy. That you can reduce your number of physical tests. You can do thousands of these tests, uh, in virtual scenario. You can do all kinds of design optimization. You can do whatever you want. All it takes is time. And nowadays, even industry wants to reduce that computational time as well. So computers are getting faster and faster. So many different algorithms and codes are being developed that can process this. Methods are being developed, that can reduce the processing time, because finite element of a car, element model of a car will have millions of elements, and then you will add a dummy to it, the anthropometric testing device inside, and all that. It will increase the number of elements and nodes, and it will exponentially increase your processing time, etc. So it's even more important for you to understand these things in a virtual environment, and when you do it, it's extremely helpful. It helps the physical test. I have given just two examples of existing standards, one for the US and one for the India, but you can read here. The reference of these images is called it's a book called Safety Vision 2020-21. It is published by an institution called CAR HS, and it is, you can download it for free. Let me just show you. It will look something like this. Yeah, this is the book. It will look something like this. Uh, and it gives you a very good brief about all the existing criteria in different countries and different and it has lots of details in it, and you can just peruse it. You can just go through it. It's it's free for everybody. They update it every year with new additional standards that are being used in the industry. And so you can see there's a picture. It's very helpful. So what kind of impact this is? This is the frontal impact. It's a moving deformable barrier. It's moving to this barrier here. You see, it's a moving barrier. These are the wheels, and this will also move, and the car is also moving. So both are moving. Car is moving at a 50 kilometers per hour, and it's deformable barrier. This square block here it's deformable. It's actually honeycomb structure, you know. So basically that will also absorb some kind of energy. So basically imagine that it's a car in front of you, you know, and your structure is also going to absorb some kind of energy. These two that you see here are two different kinds of dummies. We'll talk about them in a while. And these two here are the passenger child dummies, you know, and this is how testing has to be done. This is the protocol. This is how it has to happen. And when you do this kind of testing, whatever injury signals that you will get, accelerations that you will get, forces you will get from these dummies, they cannot exceed certain limits. When you are within those limits, you can say your car has passed. When you cannot stay within those limits, even a single signal, you will lose points for that. You know. So here it says what kind of regions that they are looking at. The head and neck. Let me just put it. So these are the regions, points for each mode. So these are the point. These are the regions they are looking at it: head and neck, chest and abdomen, pelvis, femur and knee, lower leg and foot. That's it. You know. Now this is even more. You know, it's exhausting. You know, it's very difficult to maintain everything at the same time, and it's very challenging. Now here you can see that what I have given a little bit information about the USA, the FMVSS standard that we talked about. It's called 208, FMVSS 208. These are the frontal impact scenarios, you know. Uh, so you can see there are 4 different scenarios that you should be testing your cars for, and there is one offset frontal. This is relatively new offset frontal because this standard has been added after a lot of research on the accident data. So there are a lot of research companies who collect the accident data. There is the actual field called accident reconstruction, you know, who would go to the site of accident, and they will try to reconstruct the accident. They will try to see how exactly the accident happened, from where the car came and where it could have impacted, and how it could have, you know, uh, slided or rolled over or whatnot. So this, after studying lots of those data, they have added this offset frontal. So it basically replicates. You see a car stopping right in front of you, you know, very sharp brake, and you see them braking, and you try to, you know, swerve. You try to avoid them, but you cannot avoid them completely, and you just, you know, touch them at, you know, 40% or, you know, 20% or 10%. You just touch them, and what that does. So what frontal impact, full width frontal impact is basically linear acceleration. You know, a car is directly hitting into the barrier, but this offset will do, it will rotate the entire car. So that will add the huge angular acceleration. It makes the scenario so much complex. India did not have standards for a very, very long time, and good for us that past 2 years they have started coming up with their own scenarios. Now, these scenarios that I just talked about, they are based on the real accident data. So that is regions. US will have different road traffic behavior, and India will have a different road traffic behavior. You know, so for that you need a very exhaustive study of how your citizens are using roads, what kind of traffic laws they are following or are they not following, how do they drive, what kind of awareness do they have, lots and lots. India is still working on those kind of research. It's still collecting data. If you might have heard of companies called JP Research, and Tata is doing some research in this manner, and they are collecting a lot of data. You might have seen somewhere in Mumbai Pune highway. I think in Coimbatore also they are doing collecting this kind of data and trying to understand the behavior. Sadly, in India, what happens in many of the road traffic highway incidents, many of the truck and car incidents, the drivers tend to run away from the truck drivers tend to run away from the scene, and that basically assumption of the guilt, you know. So the first responders are the police department, and they always put driver's fault, even though infrastructure may be at the fault, but since driver fled the scene, it's assumption of the guilt, and infrastructure is not great. The truck drivers or many of these lorry drivers, etc., they are not paid very well. They are overworked. They work in a very long shifts, you know, so they are not in a good mental health, drive at night or different conditions. So these are a lot of factors, and one must be aware of these factors in understanding and looking at the statistics that comes to you, you know. So this is one reason why India is still trying to work, you know, in this field, in the accident collection and understanding the behavior, road traffic behavior of Indian accidents, etc. So this is why it is taking long time. We also have a big done to start it off with. They have taken example from the Europe and United States. You know, you can see here the only the one of the major difference is the side of the barrier. It's different because driving side is different in India, and in US it's different. You know, steering wheel it's on the different side of the road. You know, we drive on the left and we drive on the right, so it's different. Uh, so this is how they have taken things into consideration, the speeds, etc., etc., and they have come up with the standards. And these standards they evolve eventually. Uh, so there's just an example of how do you get your safety rating. You know, so do you remember we talked about the head injury criteria? It's called HIC 15 because 50 millisecond clip, time clip they take. So you can see here that if you can achieve, uh, if you are more than 700, you get 0 points. That's it. If you're less than 700, you will get some points. But if you can get less than 500, you'll get 4 points, 4 star rating. You know, so achieving this 500 is extremely difficult, and this is just one standard. You know, you should have these all the other standards well within the range to get the all 4 star. So you can imagine how difficult that is. And that is not just that, you know, there is just one part of it, you know. What the other thing is that even if you, for example, I do my car assessment and I get my HICS less than 500, and I'll be like, I'm very happy with, oh, I got 4 points. No, that is not enough. There are modifiers here, you know. If there is an unstable airbag steering wheel contact, you will lose 1 point directly. If there is a hazardous airbag deployment, you lose the point. Incorrect airbag deployment, you lose the point. Steering column displacement, you lose the point. You know, can you imagine? You know how stringent it is. It is becoming very difficult. So, uh, so this is the time where finite element analysis, the virtual analysis, the CAE analysis is extremely helpful. You know, in doing thousands of simulations, hundreds of simulations, and come up with the best optimized solution for it. You know, here's just an example. If you want to know more about this, please go check out this book. It's freely downloadable. You can read through it. Lots and lots of information is there. uh, I think it might be very interesting for you. Now, what kind of tools that are being used? Now, you can do this physical testing, right? But what is the best way of doing the physical testing? You know, you need a physical hardware. So they have developed something called hybrid dummy. You know, it's called hybrid because it has its own history. You know, we can do probably a different a whole seminar on how dummies were developed, and it's very exhaustive. You know, years and years of study has been on. What you see here are the dummies. This one here, the big one, is a hybrid 3/50th percentile dummy. Now, it's a male dummy. Now, uh, there is a little bit statistics involved here. So for the male population, so for example, you take a region, for example, United States. You measure the anthropometric data of lot of people. You come up with the sample size. You measure their height and size and different dimensions of their body, and you pattern you know, you do statistical analysis of it, and it found that average male population were at the 50th percentile. So what were the dimensions of that average male? So they came up with these dimensions, and based on these dimensions they decided that it should be this, the height of this dummy should be this much, the chest size should be this much, the head circumferences should be this much, the upper arm and the lower arm, the upper leg and lower leg, their sizes should be different. This is how they come up with. When it comes to male, they always talk about 50th percentile male, the maximum population. It is represented by the 50 percentile average. When it comes to female, the smaller dummy here, it's called hybrid fifth percentile. So you can imagine that average female population is much smaller. You know, no, so that's how they come up with. Now each country will have their own different anthropometry, and they were the only manufacturer. Now there are some competitors, but let's see where it goes. They have lots and lots of Humanetics has lots and lots of experience in developing hardware of these dummies, and these are extremely expensive specimens. They are very expensive. So here you can see this is the THOR 50th male. Now hybrid is the dummy very popularly used, and THOR is nothing but the upgrade of a hybrid. How it is upgraded, we will talk about it. Even dummies are now upgraded. In today's time, even dummies are upgraded uh, to make them much more sensitive, much more sensible. Now, so let me just talk about. So these are the dummies. They are called ATDs, or anthropomorphic testing devices, or dummy models. There are hardwares. What you can do is they do a FE model of these hardwares also, and use them for the CAE analysis. Similar case study I would like to show. It's called development of THOR 5th female dummy model. Now, I was one of the co-author of this paper because I was a part of a team which developed the FE model of this THOR 5th female dummy. Now this is the hybrid, and this is THOR. So from outside you can see there are a lot of differences, in their body structure, and now we will. So what was the major motivation behind this upgradation? Now, one of the major is that they wanted to include certain complexity. So for example, the thigh region here is more accurately represented in the THOR 5th female. Also, the rib cage is also more accurately represented in, and also they have added the offset frontal crash test that we just discussed here, right here, which will add a lot of angular acceleration, So you need a dummy who can be used to assess those kind of angular accelerations, So that was one major upgrade. And how exactly it works, yeah, we'll talk about it. Just next slide. Now we developed the FE model for this dummy. So we had our own challenges in developing this FE model. So this is the FE model. This is what it looks like. Again, if you want to read this paper, you can check out this link here. It's an open, it's open source. You can download. You can read through it. Now you can see how accurately it is represented in FEA. There are 0.6 million elements more, and zero point 0.5 million, almost 0.5 million nodes, and time set is close to 0.7 millisecond. And it's very important to maintain such kind of time step, because you want it to be faster. And you can see here that this rib cages, what these small lines are going slant. These are nothing but the ribs of the rib cage. Now, hybrid did not have these slanted rib cages. They had much more straight, but actually human body is not like that. It's slanted downwards, you know. So that's the one complexity. This is in hardware, mind well. In FE, it is very easy to capture geometry accurately. It's hardware, it's very difficult. But it's done in hardware, And measurement of chest deflection, how chest is going to compress. The measurement in hybrid, it was very easy. There was just one instrument here, a straight instrument. You just measure the compression and you're done with it. But now this is slanted. It's not so easy, And now you are going to use it in offset frontal barrier impact. There is going to be angular acceleration, So it's a much more complex movement. So they came up with a mechanism called IR track. So it can measure the 3D in physical hardware. It can measure the 3D displacement, and based on that, you can, calculate your injury criteria. So it's very advanced tool. It's very advanced machine, and we developed the FP of it. Now, and we had a fortune of developing FE before the hardware was developed. We just had the CAD designs, and we just developed the entire FE on it. And based on this paper, we gave them a lot of feedback, the manufacturing team, that what designs are working fine, which designs are not working fine. And before even manufacturing the first dummy, they knew which parts are going to fail, which parts are going to work well. It saved a lot of money to the company. Very cost effective.